Okay, students, I think some more students has to join. Okay, anyway, let us start the class. So we are going to start this fourth unit. So in this, these third unit and fourth unit are like basically for like crystallography. Okay, and it is like very basic information that you are going to learn here. Okay? Because our curriculum is not like crystallography, okay? But you guys should not miss this paper. So that's why we framed this syllabus at a basic level. But if you want to learn more, so you can read that book. So whatever the book I sent you will describe about this like structural biology like very detailed in crystallography. So you can read for more information. You can read this book. Okay? So basically, what you are doing is you are treating the X-rays, right? X-rays, and it is falling onto the crystal, and then the diffracted ray is the diffracted ray or like a scattering ray. Okay, so these scattering rays that you are recording. So these scattering rays do have the information about all the atomic details of your molecule. Okay, so you know the crystal is like a periodic pattern. Okay, so in the previous class I told you the crystal when it is forming, so it is forming a lattice layers. So these lattice layers are like a very perfect in a very periodic manner, and in this like a periodic lattices, the molecule, the arrangement of the molecule is also periodic. Okay. So as a result, what will happen? When you are exposing the crystal to the X-ray beam, the diffracted rays or the scattering X-rays, scattering rays, that also will contain a periodic information. Okay, so after recording, this periodic information will be like converted into the real molecule. Okay. So this is like a general, like a vague idea. Okay. So assume like you are going into a library. So if you enter into the library, you will see like the rack, right? So in each row, like several racks will be there, and the books will be arranged like in a very like a periodic manner. So if you start from one end and you will start walking to the other end, at both sides you will see like a continuously the periodic arrangement of the rack, and you will have like a clear vision. You will have like the library will be like a visible, very clear, because you have like a periodic arrangement. Assume like the racks are arranged in a zigzag manner. Okay, so when you cross over, when you walk over, the visibility is not clear because hello. Uncle office there, man. Under இன்னொரு நம்பர் ட்ரை பண்ணுங்க. Okay, so if you have like the rack is not arranged properly, right? So if you walk over, So some racks will be visible, some racks will be like a hidden. You cannot see the like the other racks, right? So it is because it is not a periodic arrangement. Okay, so same thing. So a proper crystal, a single crystal, it will be having like a periodic arrangement of the molecule, whereas the mosaic crystal, okay, the mosaic crystal, the arrangement of the molecule is not periodic. Okay. As a result, the diffracted, from the diffracted X-rays, you cannot get like any clear information. Okay, so this general idea. Okay. So here, like you have like two important basic equations in solving the crystal structures. So one is like you have to find out like a structure factor, and another is like a electron density. Okay, so the structure factor is indicated with capital F. Okay, and it is like a subscript F, like a small HKL. Okay, HKL indicates the reflection. Okay, so the structure factor is the measurement of the amplitude of the reflection from the set of planes HKL. Okay, so it is a function of the reflection indices, and the position of the atoms in the unit cell. Okay, so you have like an atom which is surrounded by the electrons. Okay, so when the X-ray is coming, right? So assume like you have some atom like a carbon. Okay, so around this you will be having electrons here and there, right? So you have like an electron here, an electron here. Okay, so an electron here, another electron here, right? So when X-rays is coming, okay, so when X-ray is coming and it is hitting this electron, what will happen? So assume it is reflecting. Okay, so you will have some reflected X-rays. From here, you will have a reflected X-rays. Okay, so here you will have like a reflected X-rays. Okay, and in the molecule, you are not having only one carbon. You will have like thousands of carbons, right? You will have like thousands of carbon. So in each carbon, you have like electrons. So the diffracted X-rays, it is from the thousands of electrons. Okay, the scattered X-rays is from thousands of electrons. All right. So here it is the measurement of the amplitude of the scattering X-rays, the reflection from light set of planes. Okay. So function of the reflection indices and the position of the atom in the unit cell. So then you are going to see the electron density. Okay? So electron density is a Fourier series involving the structure factors. Okay. So this is just like introduction. We will see these things like clearly in following classes. Okay. Assume like we are actually now we are going to the wave here, right? So since we are dealing with like X-ray, we are going to do like a mathematical calculation. So X-ray, assume you have like a waveform, right? So we are trying to interpret this waveform into mathematical equations. Okay. So assume that point A moves on a circle at constant angular velocity. So here you have like a which is moving along the circle at angular like constant velocity. So its projection on x-axis. So here is like x-axis, point B. Okay, so this is the point B, is set to execute like simple harmonic motion. Okay. A plot of linear displacement of B as a function of the angle phi of radius vector f. Okay. So here is like a radius vector f, simply the cosine function. So I can say like a OB. Okay. So OB is equal to f cos phi. Okay. So the maximum displacement is equal to the magnitude of like f, which is defined as the amplitude of the wave. Okay. So maximum like displacement, I can say it is like an amplitude of the wave. Okay. So cosine function. So here this is the cosine function as a representation of like a simple harmonic motion. So wave with amplitude f and phase angle delta. So you can see like this is like a wave shifted to an angle of like a delta. Okay, and its like amplitude is like f. A wave like this is like characterized by like two quantities, amplitude and phase angle like delta. Okay. So the plot of linear displacement as a like function of the angle phi for a simple harmonic motion. So f and delta characterize the vector length f in a complex plane, making an angle delta with positive real axis x. Okay. So here f and delta characterize the vector length f in the complex plane, okay, making an angle like a delta. Okay. So here it is like a and here it's like B. So we can describe the wave in equation as like f is equal to a plus ib. So this is like a complex number, you know that. So a and b are like the real numbers and I is the like imaginary. Okay, so it's indicating like a complex number. So complex number can be represented by polar coordinates r comma delta. So I can rewrite this like a plus ib is equal to f of cos delta plus I sin delta. Okay. So here this a plus ib, I can say it's like a rectangular form, and this part is I can call like a trigonometric form or like a polar coordinates. Okay. So I can, since it is like a complex number, I can take the magnitude like modulus f is equal to square root of a square plus b square, and delta I can write like delta is equal to tan inverse of d by a, and a minus b is a complex conjugate of like a plus b. So absolute value of a complex number is the product. So a plus ib, a minus ib is equal to a square b square, a square plus b square. So as I told you in previous slide, so you have like some atom something, and you have like surrounded by like this so many electrons, and the scattering is from like each electron. So you will have like thousands of like atom like this, right? So in that case, you will have like a huge number of electrons. Okay, so the emitted, okay, the scattering X-rays is a resultant of the scattering from all the electrons, okay. So in that case, you have to sum up all the scattering waves, okay. So you have like the electromagnetic radiation, you have like a crystal where you have like thousands of atoms and electrons. So from the electrons, it is scattering. You have like thousands of rays like scattering. So principle of like superposition tells us to combine the scattered waves to give the resultant wave. Okay. So in order to get like a resultant wave, you have to combine all the scattering waves. Okay. So the amplitude resulting from the simultaneous action of waves is the sum of displacement of like individual waves. Okay. So the principle of like superposition amounts to add the vectors representing the individual waves. Okay. So I have like several individual waves like F1, F2, F3. Okay. So each one is having its own phase angle del 1, del 2, del 3. So in order to find out like a resultant vector, I'm going to sum up like all the individual vectors F1, F2, F3. Okay. So when I am getting the resultant vector, I am losing the phase information. So individually, I have like a phase angle. Okay. But the individual thing with the individual thing that I cannot do anything, any calculation. Okay. So the superposition waves, right? The principle of like superposition, I have to sum up all the individual vector. So when I sum up, when I find out the resultant vector, I am getting like resultant vector, but losing the phase information. That's called like a phase problem. Okay. So the phase problem we'll see in the later classes. Okay. So here, so you can write in this way to do the resultant wave, or you can do in this way also. Okay. So you can see this is the resultant wave. So F1, F2, F3. Okay. So the resultant angle, this is the alpha. Okay. So here you can say like this individual vector F1. So this is F1 cos delta 1, and this part is like F1 sin delta 1. Okay. So here F2 is there. So this part is F2 cos delta 2, and this part F2 sin delta 2. Okay. So you have like F3 here, and this part is like F3 cos delta 3. Okay. And here this is F3 sin delta 3. Okay. So summation over J, Fj is equal to cos delta J. That is there for the resultant vector. Okay. And here summation over J, Fj is equal to sin delta J. Okay. So the picture shows the projection of the resultant vector on x and y axis are simply the sum of the component projections on the same axis. Okay. So x component of the resultant vector I can write like x is equal to F1 cos delta 1 plus F2 cos delta 2 plus F3 cos delta 3, which is summation over J Fj cos delta J. So similarly, so y component of the resultant vector is y is equal to F1 sin delta 1 plus F2 sin delta 2 plus F3 sin delta 3, which is equal to summation over J Fj sin delta J. Okay. So already we saw the magnitude or like absolute value of the resultant is like a modulus F. Okay. So modulus F is equal to square root of x square plus y square. So which is equal to, so x and y we know. So here y and you have like x. Okay. So substitute it. Okay. Summation over J Fj cos delta J whole square plus summation over J Fj sin delta J whole square to the power half. Okay. And the phase angle alpha is equal to tan inverse of summation over J Fj sin delta J divided by summation over J Fj cos delta J. Okay. So far, is it clear, students? Students, are you able to follow in?
Yes, sir.
Yes, sir.
Okay. So the next thing is we have converted wave into like the equation form. Okay. So next thing is we are going to do the calculation of like a structure factor. Okay. So maybe I will stop here. Okay, so we will continue in the next class. All right. I think if I do it like continuously, you may like confuse. Okay, so I will stop here. So we'll do it by tomorrow. Right? Okay, guys.